Okay, we're going to move on from that now to something entirely different. We're shifting track to the story and the research we thought it was so important to bring you this morning. The human brain, right from the stage of it being formed inside the womb, this organ determines who we are and how we think, how we feel, what we decide to do. But what if we could open its mysteries as early as in the second trimester? What if we could see with incredible precision how a baby's brain begins to take shape? In a breakthrough, researchers at IIT Madras have done exactly that. For the first time ever, they've created a high-resolution 3D map of the developing fetal brain. This is a project called Dharini. 5,000 ultra-thin slices of the brain have been mapped, capturing over 500 regions in mind-boggling detail. Now, what does any of this mean? What was the process used and what is the impact? We're going to talk a little bit about that right here on the show, but suffice to say, it's a huge leap for humanity. And what it's going to mean essentially is that developmental disorders like autism, cerebral palsy, learning disabilities, it might be much, much easier to sense these while the fetus is still being created. Now, there are 25 million childbirths in India each year, 1/5 of the world's total. Obviously, this innovation could help countless families, and we're going to talk a little bit more about that. It's a brain atlas that has been created by IIT Madras. Here are the statistics to just give you an idea of how huge this is. This is the largest data set in the world of its kind. It's also the only one that has been able to capture the growing brain in fetuses in this manner. To tell us a little bit more about what this research means for India, for the world, we have Professor Mohanasankar Shivaprakasam. He's the visionary behind Dharini. He's the head of IIT Madras' Sudha Gopalakrishnan Brain Center. And he's with us this morning to tell us a little bit more about all of this research. So let's go over to him first to understand a little bit more. So thank you so much for joining us this morning. It is so exciting for us to have you here to tell us a little bit more. So tell us first, what are the possible implications of this research? What could this research potentially do? Of course, it's going to be speculation for you and I, but tell us a little bit more about what you think this could mean.
So there are two fundamental implications which you will see playing out over the next several years. The first thing is, for the first time, we know how the brain in the fetus, brain of the fetus inside the womb is developing. As we know, it's developing very rapidly, especially during the second trimester. So we will know in great detail which region is formed at what time and what type of cells are there in what region. And this is the fundamentals of how the brain develops eventually when it comes to term and to a child and adolescent. That's the first implication. The second implication is what we have here is what we call the neurotypical brains, or healthy brains. Right? So now we are also analyzing and imaging cell resolution view of brains that have developmental disorders of various kinds. Right? And we are doing that again from second trimester, and we are even getting brains after the child is born, stillborn, with cerebral palsy and various developmental disorders. So when you have these baseline neurotypical maps, you will be able to say which regions of the brain at cellular level detail in developmental disorders are different, because that answers the clinical question and the medical question as to why this particular brain with developmental disorder, why is it behaving. And the third aspect of it, which is a slightly meta aspect, is because we will also have information here on the maternal data, how the mother was, what kind of environment, both medically as well as socially, she was in. We will have a clue, and when the scale of this mapping expands, when we do more brains, we will be able to also say what kind of implications does the environment and the mother have on the fetus development and eventually to a child and an adult.
Professor, can you explain to our audiences why this research is the first of its kind? So what I mean is, why had we not seen this kind of research done in the world before? Was it the cost that was a limiting factor here? Was it the kind of technology? Why is this the first time we're seeing research like this?
So, I mean, I'll take you back some time, how this work started itself. So in around 2015, Mr. Chris Gopalakrishnan, who many of us know, a co-founder of Infosys, is one of our proud alumnus of IIT Madras. So he wanted to actually seed cutting edge brain research at IIT Madras. And I still remember this discussion around 2015 in one of these meetings. He sort of said, can we do something at the frontier of brain sciences? Brain sciences is really a very challenging area because we do not understand the brain the way we understand other organs. And out of that came this project. And people were doing mouse brain mapping. Mouse is about 1 centimeter cube, about the size of a small garlic. And you're talking about a fetus brain, which is about 100 centimeter cube, and an adult brain, which is 1,300 centimeter cube. And what was the limiting factor? It turns out, and if you want to do this at a scale, you need a very high throughput, high resolution imaging platform. Now, what does that mean? So the brain is pretty big in terms of when you want to do a microscopy, right? Light cannot penetrate beyond, let's say, about 100 micron or 50 micron, which is about the size of the human hair. So the only way you can actually see the entire brain in detail at cellular resolution is you have to find a way to section these brain at very, very thin slices, right? You're talking about 5, 10, 20 micron slices. And when you section them, there's a lot of challenges. Right? The brain itself is fragile. How will you section them? And even if you section them, how will you delicately place them in glass slides? And how you stain these the way you develop a photography? You can have that analogy. And then how will you microscopically image them? And now, even if you have done all this, you have a huge amount of data, which is in tens of terabytes if it's a fetal brain, and it's petabytes if it's an adult brain. And how will you put it back together? And the visuals that you're showing in one way is essentially started with the brain, and we have imaged it at cellular resolution, and now you see the 3D view of the brain as is. Now, that technology platform at a high throughput, a high resolution scale was missing. So, in one way, this is a very interesting project. So, we had to do a technology advancement to build a new technology platform, which was done in fact, it was done during the COVID period, the entire COVID period. The project just started at the beginning of the COVID period, and by the time the COVID ended, we had actually developed this technology platform fully. And using this technology platform, then we started the scientific neuroscience aspect of it, which is to image these brains. So this project itself has two advancements. One is the technology advancement that, in fact, has allowed us to do this, and the scientific advancement, which is generating this neuroscience, high quality, high resolution data that's now out there for the world, released for the first time from India.
Professor, can you tell us, one of the things I read in research about what you've done is that this could potentially have an impact on AI and the way AI is developing. And that felt like a strange connection. How could the human brain and what we're learning about it in its embryonic form have any impact on AI? Can you explain that link to me?
Yeah, that's a very deep question. So, if you look at AI today, and we'll give a 50,000 feet view, when we say artificial intelligence, which are primarily made of constructing what we call as neural networks, right? Maybe some of you have heard of the word neural networks, is the way we think the brain is structured and how intelligence or how computing works even before we go to the intelligence. So the way we have a computer designed today is there is storage, then there is processor, then there is memory. All of these we look at as individual modules, and we connect them, and that's how we do computing. Now, we all know, even one look at the brain, that obviously memory, storage, and computing is not the way we have organized in a computer.
Right.
So, what would be the ultimate AI in terms of how would you create an artificially intelligent computer at the kind of power, which is about 20 to 30 watts, is what the brain consumes, and we are consuming megawatts, and we're talking about gigawatts of power to actually power all these GPUs that are around the world. So the clue is obviously inside the human brain, because the brain is obviously structured in a certain way, which we would like to know so that we can actually attempt to create the neural networks, which actually are the foundations of artificial intelligence, so that we can actually create more, first, energy efficient, and two, computationally efficient artificial intelligence. Today, what we are doing is, a more approximate and highly approximated version of what a neuron and how a neural network works. And that approximation obviously leads to a very large, rather inefficient way of doing AI, and this has been talked about quite a bit. So looking into the brain, starting from right from the fetus and how the brain adapts into a structure and gets into an adult will give us a lot of clue on how we could potentially create neural networks and build artificial intelligence systems that are much more efficient and much more powerful.
Professor, can I ask you, another thing that I read about when reading about the coverage around this story was that India had managed to do this research in a very cost-effective manner. So we'd done it at what was said to be 1/3 of the price or the amount that, for example, a Western institution would study. Professor, I want to ask you, sometimes when we talk about India's ability to be kifayati or smart in the ways it approaches technology, there's a pro and a con to it. There's also a con to the fact that we can do things at these levels. I just want to ask you, how did you manage to do this, and how do you see that sort of that critique, that we do manage to do things at cheaper prices, but sometimes that's not the best part of our research? What do you have to say around that?
Yeah, so if you look at this particular data, and this is released publicly, I mean, it's out there, you could actually see it on your phone, and we have wanted to make this public for two reasons. First is we want the world to have access to this high quality neuroscience data.
Right.
And we would not have put, and we were never planning to hold this data back, and we would not have put unless it's an absolutely high quality data. And this is today being viewed by researchers all around the world. We just concluded a fetal brain workshop last week with researchers from almost 7 or 8 different countries. So this is the largest high quality second trimester fetal brain data. Right? I mean, that as the journal, which is publishing this Journal of Comparative Neurology, we had the editor, Dr. Susanna, who's in India this week. She has written a very detailed editorial about it. And the first part of your question, how are we able to do this at a cost? It is actually has to do with the technology automation. Yes, it is not to do so much with, things are cheaper in India. So that's actually not the case here. Because we have built a technology platform which can do this at scale. So when we say scale, we can actually, to an approximation, we can actually section an entire adult brain in less than a month.
No, but tell us, just to understand that a little bit more, Professor, how much time does that usually take for us to understand how much shorter 1 month is?
Right. So typically, you will see this probably being done in several months to even a year.
Wow. Okay.
Right? And fetal brain, we are able to section and convert it into a 3D volume in few weeks to months. Right? This includes the sectioning and then the staining and all the way. So it is the technology platform and the automation, right, that actually makes us do it at a faster rate. And because it's faster, the cost comes down. Wow. It's not the cost is down because, we have made it cheaper. It has actually been, so that's how technology works. You do it at a certain scale and you're able to automate, then the cost comes down.
Professor, if I could ask you lastly, what's next for this organization, for Dharini, for the library? What do you see as the next stage of this research?
Yeah, as we say, actually, this is really the beginning of the beginning, I would say. We have started with fetal brains and we have close to 220, 230 brains that we have acquired, starting from gestational week 14 and all the way to 90-year-old with Alzheimer's, Parkinson's, various neurodegenerative conditions. So we are imaging these brains across age groups and across disease conditions. And we intend to make all of this as a public resource for everybody. So this is the first aspect of it. The second aspect of it is what you have seen is the maps and the atlases. Right? So now the medical and the clinical findings, well, when you look at these images and you correlate them with clinical conditions, and that work has started, that will actually produce clinical findings. The third aspect of it is we are also doing deeper molecular level analysis in certain regions of the brain beyond the cellular level detail. So those are the three directions and advancements that's going to happen, and we will be continually releasing these results over as and when they happen.
It's already the biggest library of its kind. Professor, your research, I know you already know it's path-breaking, but it's so incredible to hear about it here on the show. Thank you for breaking it down for us, for making it so easy for us to understand. Congratulations and good luck on all of the further research for you and the students who are researching with you.
Thank you, Toya. Thank you very much.
Okay, let's take you, our audiences. We hope that's given you a positive, inspiring start to the way you think about research in India and the way you go about the rest of your day. Let's